In this video, we're going to look at an example where we're trying to set up the area between two curves. But the setup ends up being a little bit complicated. Because of this, I'll then show you an alternate way to set up an integral that represents the area between two curves. So we'll be focusing on this example. We want to set up an integral that represents the area of the region bounded by the curve x equals y squared minus 4 and the line y equals x minus 2. So let's draw these curves. Y squared minus 4 is the parabola that starts at x equals 4. It's shifted over to the left by 4 and extends to the right. The line y equals x minus 2 has an intercept of -2 and a slope of 1. All right, so these are our two curves here. And we're trying to find the area in between these two curves. Well, the one thing special about this example is that there's going to be some change based on how this region is bounded. So if we look at this line right here, which will end up being the y-axis, and we look to the right of it, the region that we're interested in is bounded above by our parabola and bounded below by the line. Okay, so we'll be able to compute that area by looking at the parabola minus the line. But over to the left of this curve, of this line, the y-axis, the region is bounded above by the parabola, but it's also bounded below by the parabola. So you can see this change happening at the y-axis. To the right, it's the parabola minus the line, but to the left, it's the top of the parabola minus the bottom of the parabola. So what we're going to have to do is set up two integrals in order to figure out this area. And you can see it changes right here. This is going to end up being the y-axis, but this is where the two curves intersect, which we can find by setting the two curves equal to each other. Okay, so let's figure out what that point is. We'll set the two equal to each other. Now, things in this equation are solved for x, and this one's solved for y. So you got to be careful when you're solving. I think it's best to keep things in terms of y, so we don't have to solve for y in this equation over here and get a plus or minus square root. So I'm going to keep everything in terms of y. And my first curve, x is equal to y squared minus 4. So I'm going to plug that into my line. So if x is equal to y squared minus 4, I plug that into the line. Y then is equal to y squared minus 4 minus 2. And from here, I'm going to solve for y to see where the curves intersect. So this becomes y squared minus 4 minus 2. And then I subtract y on both sides. From here, I can factor. And I'll get that the two curves intersect at y equals 3. Oh, I'm missing a plus. So these intersect at y equals 3 and y equals -2. So these are the y values, these aren't the x values. If you want to find the y values or the x values, you can plug them into either one of the equations. This one's a little bit easier. So when y is equal to 3, I can solve for x. X is going to be equal to 5. When y is equal to -2, I can solve for x. X is going to be equal to 0. So that's why I drew this on the y-axis. I already knew that this was x equals 0. Your graph may not have been perfect. It may not have shown that, and that's fine. But this is x equals 0 where they intersect. And they also intersect at x equals 5, which is this point right here. Okay, and I already know, based on the graph of my parabola, that this is x equals -4. So from here, I can now set up an integral that represents the area. To the left of x equals 0, it's the upper part of the parabola minus the lower part of the parabola. So what I can do is I need to solve for y in my equation. So I have y squared minus 4 equals x. I'm going to solve for y. So y is equal to x plus 4, y squared is. And from here, I'll take the square root, so y is equal to plus or minus the square root of x plus 4. So when I express it in terms of x, you can see my upper part of the parabola is the plus square root of x plus 4, and the lower part of the parabola is minus square root of x plus 4. So to get this region right here, I'm going to look at square root of x plus 4, the positive piece, and I'm going to subtract the lower part of the parabola, which is negative x plus 4. Okay, so that will give me my region here in white. And now I'm starting at x equals negative 4 and ending where it intersects with the line, which is x equals 0. If I integrate that with respect to x, that's going to give me that region over there. For this region, I have the parabola minus the line. So my parabola, and it's the upper part of the parabola, is going to be positive x plus 4. And then I'm subtract the line, which is x minus 2. And here I'm starting at my x equals 0 and ending over here, which is x equals 5. So adding those two integrals together will give me the full area in between these two curves. Okay, so a lot of work, but this is the setup. Notice I have to have two integrals. There's no way to combine the two. And the first integral is the top of the parabola minus the bottom of the parabola. And then the second integral is the top of the parabola minus the line. Okay, so as you can imagine, if I was going to try to evaluate and find the actual numerical area, these integrals are going to be pretty complicated. We have square roots in them, plus there's two of them. So fortunately, there is an easier way. This particular integration is set up in terms of x. We can do a similar thing, but focus on the variable y. So here's the statement. Let's say we want to find the area of the region between two curves, but it would be nicer to keep it in terms of y. So we have an equivalent formula, but given this time instead in terms of y. So we have some function f in terms of y and a function g in terms of y. And we can do the same thing. If f of y is the larger function and g of y is the smaller one, then we subtract f of y and g of y and evaluate this integral from c to d if c is where we're starting the region of the area that we're trying to compute, and d is where we're ending the region. Okay, so let's go back to that example and I'll show you how much easier it is to use this formula in terms of y. Okay, there's going to be a single integral that represents this area. And we're going to do this by keeping it in terms of y. So let me remind you of the graph. So we had a graph like this, our parabola, and then we had this line right here. And we're trying to compute the area in between. If we express it in terms of y, instead of having vertical rectangles that we're summing up over, we're going to have horizontal rectangles. So essentially, we're going to compute this area by looking at these rectangles like this. In terms of y, it's going to be the function that's to the right minus the function that's to the left. Okay, the one to the right will be the larger function and the one to the left will be the smaller one. So if we want to compute this area, you can see horizontally nothing changes. The line is always going to be to the right and the parabola is always going to be to the left. So we want to have the line to the right, but remember it does have to be in terms of y. So here we'll have to solve for y. X is equal to y plus 2. So we have our line on the right, that's the larger function, minus the curve on the left, which is already expressed in terms of y. This is our parabola. So we have the line minus the parabola. We're going to be integrating with respect to y. And we want the region, and it starts down here and ends up here. So we have to figure out those y values. Well, we already figured them out before, if you recall from the previous example. So we did that by setting the two equations equal to each other. So it was a y equals -2 and y equals positive 3. And that's it. Do you see how much simpler that is? So if you have a problem where things maybe change, which function's on the top and which one's on the bottom, one thing you might do is instead express the area in terms of y. In that case, it's possible that things will be a little bit simpler, like in this example. Okay, so this is just the setup for the area. And if we're just asked for the setup, you don't have to evaluate the integral. You just simply express the setup, no simplification required, and this is our answer.